Our next speaker is Chris Strom. I was actually a little mean to Chris. I put him between Yehuda and Ilya. So please don't be too hard on him. Chris is from Baltimore, and many of you may have heard of SPDY. It's a way to make your web applications more performant. So Chris is going to talk to you about how to do just that. Thank you, Chris.
Thank you very much. Thanks for the introduction, and yeah, really, thanks for the positioning. It's wonderful. Between these two guys, how can I go wrong? First thing you want to know about me is that I like crayons. I like drawing in crayons. I like doing my diagrams in crayons. I like doing my presentations in crayons. Just that kind of guy. I don't have any access to Keynote or any of that kind of fancy, kind of artsy stuff, Photoshop. I run Ubuntu. I might have a MacBook Air, but I run Ubuntu on it, so kind of low-tech, I guess, is the way to look at it. Woo! Solidarity, brother! Solidarity! I wrote recently the SPDY book about the SPDY protocol that I'm going to be talking about today. A lot of the slides from today are in the SPDY book. Don't buy it yet. Wait till the end. Also working on Backbone recipes. It's recipes with Backbone. I'm working on that with Nick Gauthier, one of my friends from back in Baltimore. It's really meant to be the book you read after you've gone through the introduction, after you've written your first app, how to take it to the next level. We're working on that. Hopefully we'll have that done by the end of November. That's what we're shooting for. So, SPDY. SPDY is a replacement for HTTP. It's backwards compatible with HTTP. And it still does a lot of HTTP-like things. When we start looking at some of the code that we use for doing SPDY, a lot of the things will look familiar, but it's done in a slightly different kind of way. It's interesting how they've achieved some of the stuff that they've done. But if you take nothing else from this talk, take this away, that SPDY is optimized for page load time. It tries to make your pages load as fast as possible. Any other preconceptions you might have about what SPDY is, what SPDY does, how it operates, if it doesn't serve page load time, if it doesn't try to get the pages out as fast as possible, it's not built into SPDY. SPDY is optimized for page load times. By way of introduction to SPDY, I want to tell you a tale of two websites. And this is brought to you by httparchive.org. If you haven't seen httparchive.org, fantastic resource for going out and collecting stats and trends on thousands of websites that are out there. And it does it over the course of time, so you can see that, in order to be able to roll up all the trends that might be out there. Shows you what kind of JavaScript frameworks are being used, what kind of sites are using Flash, all that kind of interesting stuff. One of the really neat things it does is it takes snapshots of web pages. I do like crayons. It takes snapshots of web pages as they load in the browser. And you can go back and look at this one. This particular site, it's mystery site number 1. This is from back in July. This is accessing the website back in July. And for the first half second, it's a blank page. Not too surprising. Half second, it's barely had the time to send the request out to the server. Not much has gone back. Second later, still nothing. We're still happy, sunny skies. We're excited about this. One of our friends twittered about it. It's an exciting new site we have to look at. Okay, fine. We can wait. Half a second, maybe not so sunny skies are starting to get a little antsy. 5 is starting to set in at 2 seconds. 2.5 seconds, starting to get really antsy. And it might think I'm a little disingenuous by making this at half-second intervals right here. But if you're not measuring your page load time in half-second intervals, you're not measuring it. You're doing it wrong. You need to be able to get the web page out to the user as fast as possible. That means measuring the time in tenths of a second rather than in seconds. It's not good enough to say, I think the page will get out there by 5 seconds. You need to measure it in tenths of a second to be relatively sure that no matter where the user is on the internet, the web page will get out there. So continuing on, 2.5 seconds, 3 seconds, 3.5 seconds, we're still staring at a blank page. Now, we might be talking about a backbone application, something that's heavy with the client UI, who knows, I'm not really sure what's going on here. Keep going on, 4 seconds, rain's starting to set in, and at 4 seconds, 38% of broadband users are just going to close the website. They just don't care anymore. If you haven't even shown them a single thing, they're going to just click the little X, move back on. I've got work to do. I've got Twitter to tweet and all that kind of stuff. Another little known fact is that if you put precision on percentage on statistics, people will believe you. I didn't make that up. There's actually a study out there that said it's 30% or 33% or something like that. But by bumping it up to 38%, you really believe that. That's what I want you. I want you to really believe that I'm researching this stuff. I'm not just making this stuff up. There's stuff out there. But all I know is that if a website's taking 5 seconds, 6 seconds to respond, I've got better things to do than to wait around for that to come back. And I'm not going to take the time to go on to the next pages on the website. And I start to think about this as, the spinning, the little throbber spinning on the tab is costing me money. It's costing me money not responding back to potential clients, to existing clients. It's costing me money. So I want to be able to respond as quickly as possible. So 4.5 seconds, 5 seconds, we still haven't gotten anything. I've closed that web page. I'm done with this. I'm done with that site. I'm going to unfollow my friend for suggesting that site on Twitter. I'm moving on. It's just freaking crazy. And this is not a website from back in 2000 or before the back in 1999 or whatever. This is a site from January of 2011. It took 5 seconds, and it's still just a blank page. Site number 2. Tale of two sites. Site number 2. Deep cleansing breath. It's going to be better this time. It's going to be better this time. Deep cleansing breath. 5 seconds. 1 second. All right, we're kind of off to a slow start. 1.5 seconds. This is Amazon. 1.5 seconds. Almost the entire page is rendered. Just boom like that. HTTP archive has some nice little ability to go down to the tenths of seconds, so you can see how that comes in a finer resolution. But in 1.5 seconds, I'm ready to do what I came on Amazon. I'm ready to go. I've got the sidebar. I've got the search bar. I've even got the Kindle. I know how much the Kindle costs. I can do all sorts of stuff on here. The only thing that's not done so far is some of the ads on the side. It's no big deal. Amazon knows that it needs to get the selling stuff out as quickly as possible. The entire page takes 4.2 seconds to render once you get all that advertisement stuff all on the left side. 4.2 seconds to do that. Amazon, 4.2 seconds, a little under 500 kilobytes worth of data, 75 requests, 75 resources that need to load in there. CSS sprites, JavaScript, analytics, 75 requests go into building up this web page. And they're able to do that in 4.2 seconds for the entire thing. And more impressively, 1.5 seconds to get most of the stuff that's out there. Our mystery sites, I don't know how long it took, because I've closed that one, brother. I'm not going to wait around to see what's going on with that. I do know from HTTP archive that it took a little over 800 kilobytes worth of data and 83 requests. It's not that much different than Amazon. So, it's tempting to think that, all right, maybe this website is problematic. Maybe it's just the data. There's too much data. Maybe they're not doing CDNs. Maybe they're not using CDNs. Maybe they're not compressing they're not using the asset pipeline. But they are, in fact. This particular website is using CDN, and it's compressing its assets. It's compressing down the CSS, compressing down the JavaScript, and it's still taking this long to load. And it's not an aberration. On the average, most websites are the average according to HTTP archive. 800 kilobytes worth of data, and same number, 83 requests for most average websites. Seems like a crazy number, especially if we're using CSS sprites, if we're combining our JavaScript, combining our CSS. 83 requests, that's crazy. But there's a lot of analytics, third-party code that needs to go in there. 83 requests is pretty typical of websites. So the question we want to ask there is, how does Amazon do it? The way that Amazon does this is they optimize the order of styles and scripts, they minimize request size, they avoid CSS import, they enable compression, they minimize redirects, serve resources from consistent URLs, they specify image dimensions, favor async resources, remove query strings from static resources, avoid bad requests, parallelize downloads across host names, and minimize DNS lookups. Thank you. There's more. They also put the CSS document head, minify JavaScript, minify CSS, serve static content from cookieless domains, combine external JavaScript, combine external CSS, combine images into CSS sprites, optimize images, leverage browser caching, specify vary accept encoding header, specify cache validator, serve scaled images, minify HTML, and specify character set early. Got all that? I don't have all that. And I don't even know what some of those things are that's in it. But Amazon does. They've taken the time to learn all those rules, and a few others that aren't even in there in order to make their site load in 1.5 seconds. This other site didn't do that. You could say that Amazon does this by doing HTTP optimizations. I don't think that these are HTTP optimizations. These are HTTP workarounds. So working around limitations of HTTP that we've come to know over the years. HTTP is antiquated. I don't mean that in a derogatory sense. HTTP has been fantastic. It's been fantastic for me, for livelihood, and for lifestyle. The things that we've been able to build, the things we're able to buy and do with HTTP, it's fantastic. Most of us wouldn't have jobs without HTTP. And I'm still looking forward to things like Steve Klobnik's REST book that's going to come out. And this was all back in HTTP 1.1, so I don't want to disparage it. It's just that it's 12 years old. The web has evolved, and HTTP is not. HTTP is old. HTTP is so old. Awesome. I didn't know I'd be able to get you guys to do that. Awesome. Thank you. Good crowd. This guy was president when HTTP 1.1 came out. We had not been inflicted with the first or the second trilogy of the Star Wars when HTTP came out. This guy was not on TV for the first time, let alone the second time when HTTP 1.1 came out. Wikipedia wasn't around. This was the state of the art in technology, handheld devices. I had one of these. I had one of the modems you could hook up to these things. You plug in the phone line. I could SSH to my servers in order to do stuff. Awesome. Love those things. This was the best that Apple had to offer when HTTP came out. And Ubuntu was not out yet. It was not going to be out for another 5 years. How can you build the internet without Ubuntu? So SPDY. Let's talk a little bit about SPDY. And it offers nothing new. Fantastic. I'm coming here, this SPDY, it's got no new ideas. Why am I listening to this? Well, it's taken those ideas from the last 12 years, all the lessons we've learned, all the workarounds that we've learned for the last 12 years, and it's bundled them up into a protocol. And then what the SPDY authors did is they figured out how to make that backwards compatible with HTTP as best as possible. And then they tested the hell out of it. They tested the hell out of it because anytime you're using the Chrome browser with Google Web Services, you're using SPDY, whether you know it or not. You're not making HTTP connections to the Google Web Service. Gmail, Google Search, Google Reader, anytime you're doing anything on Google, it's going over SPDY. By the time this goes to the IETF as a draft recommendation, it's going to be the most tested protocol in history because they've been getting all this feedback as people have been testing it unwittingly, but for the benefit of Google, hopefully us, and certainly for the benefit of the users because things are much faster. So it's tempting to think, all right, do we really need another protocol? HTTP is fine, maybe bandwidth is going to save us. But in a couple of years we're going to have 6G and we're going to have gigabit Ethernet coming in. We don't need to worry about this. We'll just hang out until bandwidth is going to save us, until bandwidth comes along and saves us. Turns out bandwidth doesn't matter, not for page load time. Once you get around 3 megabits per second, it has no effect, virtually no effect on page load time. If you want to know why, there's a great Google white paper on this. I'll talk a little bit about why this is, but there's a really good Google white paper that goes into some pretty good depth about why this is. So, bandwidth is for downloading Ubuntu. It's not for downloading the Ubuntu web page. If we go, it's nice to have 3 megabits or 10 megabits or gigabit Ethernet to be able to download that Ubuntu Yslow and install it on our beautiful MacBook Airs. But to get to the Ubuntu download page, bandwidth is not going to help us at all. SPDY is all about page load time. And to understand why this is, it helps to understand the internet, how the internet is built. I don't know if you guys know this or not, but the internet is built on a series of tubes. What's so bad for that guy? It's a reasonable analogy. It works. Make fun of him. It works. Anyway, the client makes a request, goes through the HTTP tube, comes down to the server. Data travels one way in HTTP tubes. It's kind of like a Stargate. Because Stargate SG1, all that kind of good stuff. No. Client sends a request to the HTTP tube. The server can't send anything back until the client has done, until it's received the complete request. Same going back the other way. It helps them look at it like this. HTTP tube's in action. The client, the server or the client will make the request, come down to the server. The server needs to do a little bit of processing, send the response back to the client. The client does a little bit of processing, says, oh, now I need to get the JavaScript, now I need to get the images, now I need to get the CSS sprites, and then it makes a request for those things to the server, and then it sends it back. You're sitting there looking at this process and thinking, how on earth did Amazon get this to work in 1.5 seconds downloading 75 requests? Well, it's not just one tube. It's a series of tubes. It really is. Every web browser, every modern web browser opens 6, not one, not two, 6 HTTP tubes in order to make the connections out to the browser. And by doing that, we're increasing the ability to request resources asynchronously. And then if you bundle in like CDNs and that type of stuff, then you're able to get even more. You're able to make 6 requests to your main site, 6 requests, open 6 tubes to your CDN, and 6 requests to subdomains and all that kind of stuff. So you can build up a lot of asynchronous resources in order to do that. And Amazon leverages the heck out of doing this in order to get their web page displayed in 1.5 seconds. Our mystery site is the same thing, but not nearly as effectively as Amazon. So, problem solved, right? No. Turns out, and all right, my crayon drawings, sometimes they lack artistic value. That's a thermometer. I realize it's bad when you have to actually put the diagram and then tell you what that is, but it's a thermometer indicating full temp. It turns out that the tubes are ordering things. If you think this is mechanical, it's all bits and bytes, it shouldn't be this way. The tubes, when they first start off, they're cold. They can't transfer as much data as once they get warm. They need to transfer a little bit of data back and forth, and they start warming up, and then they can actually transfer more data over these tubes. Think about why this is. Think about trying to transfer an image of a rainbow. So we've got the image on the server on the bottom down here. We've got the red, RGB rainbow image that we've got to transfer. And we're going to transfer them along a train track. So the first time the train, and this is a train engine. I tried many times to figure out how to draw a train engine. Couldn't quite do it any better. But anyhow, the first time the train goes out, it only takes 2 chunks worth of data right there. It takes the red and the orange. The reason it does this is it doesn't know what the bandwidth of the connection is going to be. So it takes just 2 and says, I can probably get those through and the other end can handle it. We'll see how it goes. So it takes those out to the server, it takes that back to the client. The train comes back and says, look man, I can handle a lot more than that. And the server says, well, this is how TCP/IP works. You can have 4, but you can't have any more than that. So it's fine. I've taken the red and the orange. Now I get to take the yellow, the green, the blue, and the brown. And it takes those, but we're still not done with the image. It's going to require one more round trip for the engine to come back, pick it up, and take the blue or the purple back before we're actually done transferring that over. And this is how you warm up those HTTP tubes. Going back and forth like that, eventually you get to a point where it's pretty close to the actual bandwidth of the connection, and things move much faster. This is known as TCP/IP slow start. It's an actual thing. It's congestion window, how you manage things, manage getting data around. This is a limitation of TCP/IP, but HTTP doesn't really take into account. So why not start the tubes form? We know we need to transfer this data. Why not start it off instead of doing the 2 or the 3 chunks? Why not set it off with 10 chunks? That congestion window. Why not make that congestion window longer? The thing is that we've already got 6 connections. We really do have 6 tubes that each one of those web browsers are opening. 6 tubes times 3 chunks of initial congestion window. We're already talking about already talking about a congestion window of 18. So we're already subverting what TCP/IP is trying to do with slow start and congestion and traffic management. we really want to do this further. We want to increase it to 10 and make that worse. And given the data packet rates, data packet loss rates that we're already seeing, it's probably not the best idea to do something like that, which is why Google decided to go ahead with a different protocol entirely. So speedy tubes. They get warm much faster. There's only one speedy tube for a connection between a site. There's only one connection, and it's completely asynchronous. The client can send requests whenever it wants, regardless of whether or not the responses come back. The server can send requests or responses back whenever it wants. We'll have a look at how that actually works. Speedy conversations. Send a request in whenever you want. Send the replies back whenever you want. Some other good facts about Speedy. It's built on SSL. In the age of Firesheep and those kinds of things, session fixation attacks, building things on top of SSL is good practice. You do take a hit, of course, for the SSL negotiation when you're first loading the site, but what Speedy does afterwards more than makes up for that. Since we're talking SSL anyway, there's no reason to be doing this in plain text anymore. We can't see the conversations anymore, so we might as well make them binary. We also save a little bit of space on the conversations by making them binary. We try not to send redundant header information whenever possible. We compress the hell out of things whenever we can, and we only use that single tube for transferring things back and forth. We pay that warm-up fee one time only, and then the tube that we're using for downloading web pages is just like that tube that we're using for downloading the Ubuntu Yslow. It's awesome. So Speedy, this is Speedy itself. This is the Speedy in its entirety. And really the only thing you need to know about Speedy, the two things that are the most important things you need to know about it are the SYN streams and the SYN replies. You can sort of think about SYN streams as an HTTP request, SYN replies as the HTTP response. The other stuff, some of it helps with managing those requests and replies. Some of it handles error, is there for error handling. And then you've got data. Data is actually separate from those. We'll see how that works in a second. So the current state of Speedy and Ruby. I know we've been here for how long, and we haven't even gotten to Ruby yet. But current state of Speedy and Ruby is, in a word, in order to use Speedy, you need OpenSSL generated key. It's SSL, it's fine. We can do that. You need the Speedy gem install Speedy. It's not that hard. And it starts to get a little difficult when you have to install Edge OpenSSL. You need that in order to get the next protocol negotiation. This is how it does its backwards compatibility stuff. It advertises, hey, I can speak Speedy or I can speak HTTP. If it's Internet Explorer, it doesn't know anything about NPN, so it just keeps going ahead and making HTTP connections. And the server is able to adjust to that. But if the web browser is Chrome, it says, hey, I can talk Speedy, you can talk Speedy, let's have a Speedy conversation. So the other thing that we need is Carson McDonald NPN enable the next protocol negotiation. We need that enabled fork of event machine. It's in the TLS NPN branch. There's a pull request that's open on that. If anybody here is on the event machine core team, committer team, it'd be nice to get that in there. So this is what the code actually looks like. So we require event machine, requires Speedy. It's asynchronous. Speedy's asynchronous, so it helps to work on event machine or Goliath. See how we only have right now an implementation in event machine now. So we make the Speedy handler a subclass of the event machine connection, and then we go ahead and we run that. We start that off. And there are really only three things we have to worry about: the post init, the SSL handshake completed, and the received data. First thing we'll take a look at is the SSL handshake complete. This is how we do the NPN, the next protocol negotiation, in event machine. For that, we get the negotiated protocol. This is something that Carson McDonald's branch does only. This is working with the OpenSSL, the Edge OpenSSL. We get the negotiated protocol. If the negotiated protocol is Speedy 2, then we set an instance variable saying, hey, we're using Speedy. Otherwise, in post-init, use Speedy is just set the false up there. Now we have two ways of dealing with incoming requests. One is the normal way of doing it, where it's just going to be an HTTP request. The other way is we're going to have a parser for parsing the Speedy request. And the last thing we do is we advertise the negotiated protocols that we ports, and then we start our TLS server. And when we receive data, this chunk down here, if we're using Speedy, we send the data to the parser, otherwise we just send back regular HTTP kind of stuff. So this server here will work with both Chrome using Speedy, talking Speedy, or it will also work with Internet Explorer, Firefox, what have you. The real magic comes in the on headers complete inside the parser. Go back here, sort of skipped over that in the post init right here when we set up the parser. We have a parser's on header complete. This is a callback that, the print statements are just printing out where we're at while we're doing this. First thing we do, we've got a SYN stream that came in. We need to make a SYN reply to go out. So we create an object to do that. And here's where we start to see where it's backwards compatible. I mean, the version that we're talking about in the headers that we're going to send back are HTTP headers. We know how to do this. It's very similar to the stuff we've already done. And so this way, it's almost like the Speedy is just another transport for HTTP, another way of sending out HTTP requests. So all the good HTTP REST kind of stuff that we're learning, that we're getting good at, we can still use that while we're doing Speedy. Then we go ahead and send out that, so we create that with a stream ID of 1 with these headers up there, and we send the data as a binary back to the browser. Now, the thing we haven't done here is we haven't sent any data back to the user. We just send headers back. In order to get data back, we come down here and we get a data frame, Speedy protocol data frame. The Speedy gem is from Yslow. Who's going to be talking next. So it's really it's a great way to learn the Speedy protocol if you ever want to just root through that code. He's done a fantastic job with that. But anyway, you take the data frame, also the stream ID of 1, you say the data, this is Speedy, it's just going to go through back as text, and then you send the binary data back to the browser. But we're still not done. This is a Speedy conversation. It's async. We can send packets all the time. The client, the browser has no way of knowing that we're done sending data until we send a final data fin, which is indicated by the flag of 1 right there. And again, we're using stream ID of 1 to send all that back. And that's it. That's a very simple Speedy conversation. Problem comes in, the reason Ruby and Speedy are still kind of ugh is that if you try to make a second request on this, it'll crash. It'll crash hard. If there are anybody in the room that's really good with FFI, or even just using zlib, the built-in zlib compression libraries in Ruby, could help with this issue right here. I've worked for a week trying to figure this one out. I couldn't figure it out. I documented the heck out of it, and it just crashes. And issue number 2, Speedy gem under Ily's GitHub page. All right, real quick, I want to talk about really the killer features I see in Speedy. Normal connections that are coming in from the client, you make a request for the home page, a send response back, and at this point we know, all right, we can request the images, the CSS, and all that kind of other good stuff. We have to wait a little while there. The nice thing, the really killer feature of Speedy is that we don't even have to bother doing the packaging compressing kind of stuff. We can do Speedy server push. We request the home page, and the server just sends back everything. It sends back the home page, it sends back all the images, sends back everything. And it sends it right one after another. There's no round trip time that's incurred by doing anything. It just sends all that stuff out, and it works fantastic. The way that it does that is that you've got this is the SYN stream that comes in from the client requesting the data. It's got an ID, a stream ID of 1. Then you've got the SYN reply. It's also a stream ID of 1. This is binary data. It is binary data. And this never turns into the matrix. You never stare at this long enough to really be able to read it. It's always hard to read this stuff. But then, then to actually do the server push, we create a new stream with a stream ID of 2 that's going out from the server, but we associate it with that original request. And that's how Speedy is able to do that Speedy server push. And then we go ahead and we do another request where now it's stream ID of 4, but we're still associated with number 1. And if this were a web page that we want to serve up, we've got styles, JavaScript, and 5 images that we want to send out. This is Node.js code. I apologize for doing this at GoGuRuku. I really do. But it's a nice way of expressing it. This is just a regular old Express.js resource. It looks a lot like Sinatra. We're getting the root resource right here. We're going to render the index template with a parameter of express. Pretty simple. This is where you actually do the configuration. You get the NPN protocol supported. And then we do a push right here with a simple push callback. A simple push callback is nothing more than just calling a push method on the response with those things that we want to send back out. So it doesn't need to be as complex as we currently have in an event machine. It'd be nicer, I think, to build it up on top of Goliath or something along those lines. The website, the mystery website, borders. 5.5 seconds, we finally get the masthead. Takes 11 seconds. We're still not done. Still don't see the price of the Kindle knockoff. Takes 11.4 seconds to do this. Zero, forgot it is. It's ridiculous. Thank you very much. Appreciate you having me out here.